Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and this short video is going to deal with the standard normal transformation, and I suppose it's the second video in this particular series. So this video is going to deal with the standard normal transformation. Okay, transformation. And let's just recap on what the standard normal transformation tells us. Yeah, okay. It tells us that if we have a population, okay, with a certain center point, okay, or mean value, okay, and standard deviation, that we can transform that population to a population that has mean value of 0 and standard deviation of 1. And the way we do that is through the standard normal transform formula that says z of x is equal to x minus mu all over sigma. Okay, where mu is the population mean and sigma is the population standard deviation. Okay, so let's have a look at a particular scenario. Okay, this scenario is factory workers have average earnings of €660, and we know that the standard deviation associated with them particular earnings is €35. And what we're interested in is if we randomly select an employee from this particular population, what is the probability that that particular employee earns more than €695? Okay, so the first thing that we'll always do is to try to understand the population that we're dealing with, and to understand the population we should always try to identify the population parameters. Okay, and in this situation the two parameters that we're interested in is the population mean, which is €660 in this case, and the population standard deviation, which is €35. So for this scenario, we know that the population mean mu is equal to €660, and the population standard deviation sigma is equal to €35. Okay, brilliant. And what we want to do is we want to randomly select a person from this particular population, and the question is, what's the probability that they earn over €695? Okay. One of the assumptions that we're going to make is that the population that we're dealing with is normally distributed at this stage. Okay, so because we know this population is normally distributed, we can represent this particular population and this particular scenario through a distribution. Okay, so for this particular scenario, what we know is that the population is normally distributed. Yeah, so it's a bell-shaped curve represents the population, and the center point of this particular population or this particular curve, yeah, is going to be the population mean, which is 660. Okay. Now the question that we're interested in is if we randomly select an employee, okay, that employee earns more than €695. Okay. So because this particular curve represents the population, this horizontal axis here is going to represent individual earnings of employees. The center point here represents people that earn 660. To the right is going to be people that earn more than 660, and to the left is going to be people that earn less than €660. This question is, well, what about those guys that earn more than €695? Well, 695 is greater than 660, so that should be on the right hand side of 660, and 695 is about there. Okay. We're interested in employees that earn more than €695, so they're employees to the right hand side of 695, which are the employees over here. Okay, so really what we're being asked is, what's the probability that if we randomly select an employee that they earn more than €695? Okay, well, all the employees that earn more than €695 are to the right hand side of 695. So really this question is, can we calculate the area under the curve to the right hand side of 695? I think we called these before in our previous videos when we were looking at the standard normal probabilities. We called these type 2 probabilities. We define them as type 2 probabilities. Okay, so the first thing we're going to do is, because our tables, allow us to look up probabilities associated with the standard normal distribution. That's a distribution with mean of 0 and standard deviation of 1. Okay. What we need to do is we need to transform this particular scenario or this particular curve here to a curve that's centered on 0 with a standard deviation of 1. And the way we do that is through the standard normal transformation formula. Okay. So what we're going to do is we're going to take all of our values along our x-axis here that represents factory worker earnings, yeah, okay, and we're going to pass these into this particular formula. So the first x value we're going to take is 660, okay, and actually I think what we know at this stage is that anytime we pass in the center point of our curve or the mean of our curve, yeah, that's always going to be transformed to 0. So actually when x is equal to 660 euros, that's always going to go to 0. And let's just do it once more. So x is 660, so it's 660 minus the mean of the population, which is 660, okay, divided by the standard deviation of the population, which is 35, and that gives us 0 over 35, which gives us 0. So this curve is shifted down towards 0 under this particular transformation. Okay. So what happens to 695 through an application of the transformation? So when we pass in 695, so when x is 695, this becomes 695 minus 660 divided by 35, which gives us 35 divided by 35, which gives us a value of 1. So 695 is taken to 1. Okay. So what we now know is that this particular curve has been shifted to a curve, yeah, its center point has been taken to 0, okay? So this curve now has been taken to a curve, standard normal curve. 660 went to 0, and 695 went to 1. Okay, and 1 is over here. And this horizontal axis now represents this standard normal variable z. Okay, so that's our z variable. Now in this scenario here, we're interested in what's the probability that if we randomly select a worker, that's our x, yeah, that they earn more than 695, which was areas to the right hand side of 695. In this situation here, what we're interested in is it's still areas to the right hand side. This time it's areas to the right hand side of 1, okay, because 1 is associated with 695 under the transformation. So in this situation, we're looking for the area to the right hand side of 1, which is exactly the same as what is the probability of observing a z-score that's greater than 1. Okay, so this is a right-hand tail area, which is what we have called previously or defined to be type 2 probabilities. Now what we always know is that anytime you have positive z-scores, what we should always do is look them up on our tables. So if we go to our tables, okay, what we're interested in is we're interested in looking up a 1 on our tables here as a z value. Okay, so what we're going to do is we're going to come down. This actually represents 1.00. We're going to come down to the first significant digit, which is 1, and the first decimal digit, which is 0, which is we're going to come down to 1.00. Okay, and we're going to come down to column 0.00 because this 0 here represents the second decimal digit. Okay, and we're going to look up that value. So when we go to our tables, okay, and when we look up 1.00, we're going to come down to the first significant digit of 1, which is here, and the first decimal digit of 0, which is also there, and we're going to look for the second decimal digit down the first row here, or on the first row, the first column, which gives us 0.8413. So when we look up 1.00 on our tables, we get 0.8413. Right, brilliant. Now what we know is that anytime we look up a positive value on our tables, that positive value that's returned from our tables will always represent the area to the left hand side of the positive value. In other words, the area under the curve to the left hand side of 1 is 0.8413. Now, we're not interested in the area to the left, we're interested in the area to the right. Now, when we defined type 2 probabilities previously, we developed a strategy for calculating them areas to the right. Okay? And what we said was always important to realize is that the total area under the curve is equal to 1 unit. Okay? So, if we take the shorter line away from the longer line, what we're left with is the area to the right hand side here. So in this situation, we have the longer line, which is 1, minus the shorter line, which is 0.8413, which gives us a value of, when we do this on our calculator, we have 1 minus 0.8413 gives us a value of 0.1587. Okay, And actually, we had a rhyme for this before. We said anytime you want to calculate an area in a tail, you'll always have to take away from 1. Okay? So what we know now is that the area in this right-hand tail is 0.1587. In other words, the probability of observing a z-score greater than 1 is equal to 0.1587. But under the transformation, we know that this probability is equivalent to this probability here, which is the probability of randomly selecting a worker, and that worker having average earnings greater than 695. In other words, the probability of randomly selecting a worker from this population and that they earn more than 695 is equivalent to the probability of observing a z-score that's greater than 1, which is equal to 0.1587. Okay? Or about 15.87% of the time, we'll see a worker, when we randomly select one, that earns more than 695 euros. Okay guys, my name is Jonathan Lambert, and this concludes this short video on the application of the standard normal transformation. And I hope that was informative. Once again, I'm Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and thank you.